Pat has a background, master's degree in mechanical engineering, where he definitely has focused on mostly stratigraphy. Isn't that true as far as geology is concerned, Pat?
Yes, I'll describe a little bit about the difference between a geologist and a petroleum reservoir engineer in a minute.
Sure. Okay. Anyway, he's a senior advisor with British Petroleum. You worked with ARCO for a number of years until British Petroleum bought them out. Isn't that right, Pat?
That's correct. 21 years with ARCO and now BP.
Been associated with our volunteer apologist team for some time now, and he's a great resource for us, and I'm really pleased that today he's available to share his experiences as it relates to Noah's flood, and it has to do with the whole issue that Krista's bringing up here. What does the record of nature have to show about it all, and maybe we can help resolve some of these problems. So, Pat, I'll let you go ahead and get started here, and we're all ears.
Okay, well, I got a phone call last week from Bob Stewart asking me if I could put something together on was Noah's flood global or local, and taking a look at it from the scientific point of view. And I decided to do this for several reasons. Actually, I was very excited to do this, and I'm going to walk through a couple of these reasons right now. This is really an important subject to me. I've been in the energy business now for 25 years, and I say I'm involved in the business as opposed to the science of geology and biodeposits. Now, I did some of the science end of this, especially when I was working at Los Alamos National Laboratories, but during the last 21 years up here in Alaska, it has been a business. And I'm a petroleum reservoir engineer, and we work extremely closely with the geologists because what I tell the geologists is they are interested in the rocks, and the petroleum reservoir engineer is interested in the holes in the rocks. Because ARCO doesn't pay for rock, ARCO pays for oil that they sell to you guys as gasoline, and that oil resides in the holes in the rocks. So geologists focus on the rocks, and the reservoir engineers focus on the holes in the rocks, but we are intimately involved in each other's worlds. So that's why I'm competent to address these subjects. I know a fair amount about sedimentology and absolutely nothing about igneous and metamorphic rocks. So if you bring me some kind of a hard rock deposit from Colorado, I'm sorry, I can't tell you what it is. But looking at the sediments where you might find these biodeposits, that's what I do. And having been involved in this business for many years, there were a couple quotes that really reflected kind of the dilemma I was at in the first, say, 15 years of my Christian life. And I don't know for sure if this is properly attributed to Galileo, but I believe he's the author of this quote, and that is, "The heart cannot rejoice in what the mind cannot accept." And basically, when there's a dilemma, when you just are unable to really believe something and embrace it, it's just hard to celebrate with it in your heart. And then the second quote, they asked it was our Sunday school class, and the teacher asked this 10-year-old boy, what is faith? And this 10-year-old boy said, "Faith is believing what you know isn't true." And, we laugh at it. I think, boy, this is a great quote because this expresses where I was at for the first 15 years of my Christian life. Because all I was ever taught was that the Bible says the Earth's about 6,000 years old, and all the geology came from Noah's flood, effectively. And as a professional in the energy industry, I just knew that wasn't true. So I was this it was a very disturbing place to be, and I basically had no resolution to that until 1987, and that's when I first met Hugh Ross. He was presenting the early part of the Reasons to Believe material at First Presbyterian Church in Anchorage. And First Presbyterian was about a block away from the ARCO building, so I remember walking from work several days running to see this guy because I was really curious about the subject. And I was just amazed. It was here's a guy that's a first-class scientist and also is really dealing well with the scriptures. You look at the original languages, you look at the intent of what was going on, and it became clear that you weren't necessarily stuck with the young earth, and you weren't necessarily stuck with all the geology coming from Noah's flood. And actually, you had the liberty to believe in the old earth and what I really knew to be true about this complex geology. So this was kind of like being let out of jail for me in terms of just my witness at work and my ability to be comfortable with what I believed. So Reasons to Believe had a major impact on my life in the reconciliation of the Bible with what I knew to be true in nature, and it really increased my confidence in the effectiveness of my witness with the geologists and geophysicists and engineers that I work with. Okay, so we're ready to go now. Bob and Krista asked me to take a look at 4 crucial questions: geological record, biodeposits, the fossil record, and speciation. And I basically declined to do the last 2 because I thought they probably had better people to do those. And what I decided to focus on was the geological record and biodeposits because that's what I work with. The questions that they asked me to cover were: question number 1, could the entire geological record have been laid down quickly thousands of years ago in a global flood? Question number 2, could all the biodeposits have been formed thousands of years ago in a global flood? And before I get started on the scientific end of this, I think what I need to do is to go into slide number 5 and tell you where I'm coming from on Noah's flood. And what I believe about Noah's flood, number 1, it was God's judgment on all mankind. And number 2, it was real. It really happened. It's not a figment of speech or a teaching or a legend. It really happened. The third point, it killed all mankind except the 8 people on the ark. And point number 4, which I think is important, is it killed all the animals that had been contaminated by mankind's sin. Mankind basically corrupted a lot of the animals that he contacted, so God had to take them out at the same time he took out man and his sin. What I also believe about Noah's flood, and this is what I believe as more as a professional rather than doctrinal, because I think Krista did a great job of presenting both sides of the issue, and I think doctrinally you could probably go either way. But speaking as a scientist, I believe this was a universal but not global flood. I think it was restricted to Mesopotamia because I think all of the evidence we have in Scripture says that's where mankind lived prior to Genesis 11. And then the judgment was intended for man, not animals. There's no reason to kill the polar bears in Alaska or the llamas in Peru or the kangaroos in Australia if they hadn't been corrupted by mankind's sin. And then here is a key point that I will get into a little bit later, and actually hopefully I will convince you of, is that Noah's flood, whether it was global or regional, left very little impact on the geologic record. And point number 3, it played almost no role in forming biodeposits. Biodeposits are things like oil, natural gas, coal, limestone, marble. Those are things that are formed by living organisms that have lived and died and become part of the geologic record. And then finally, you cannot use Noah's flood from a scientific point of view. You cannot invoke Noah's flood to explain a young earth. So these are the other places that I'm coming from that you should be aware of before I start. Now, before I go into the science, I want to lay out a difference in approach between a scientist and a theologian. And I really appreciate the way Krista went through her presentation because she presented all sides. You know, her focus was on seeking unity in the body of Christ. The emphasis was to major on the majors and realize, when points are small and aren't worth fighting about. And it's important that we take these subjects with a gracious and humble heart, that we not get haughty, arrogant, or combative, argumentative with each other. And that's the way theologically we need to carry out discussions. But unfortunately, science doesn't work that way. And there's a great definition of science. I should have put a slide in here. It's science is the brutal murder of elegant theory by ugly fact. Okay. And what I'm going to do is I am going to brutally murder some theories today with some extremely ugly facts. And so unlike the theologian, where we really need to be humble and gracious with one another, science is kind of a survival of the fittest in terms of your ideas and your concepts. And when ugly facts come up and blow away an argument, you just throw it out and start with something else. The major issue with the geologic record is complexity. And I'm not going to talk to you today about things like rates of deposition or radiometric dating, because those are a little bit harder to get your hands around as a layman. What I want to focus on is something that I think each of us can walk away with a very clear understanding. And that is, first point, the Genesis flood is a very simple event. It was very significant. It was divinely orchestrated, but from a geologic point of view, the Genesis flood is a very simple event. And the second point is the geologic record is very complex. And this simple flood event cannot explain the complex geologic record. And we're going to spend the next half hour or so just looking at why that's the case. If you take a look at chapter 7 in Genesis, you'll see that what's being described is a monotonic, which means a steady increase in seawater level. This water is not going up, going down, going up, and going down. It's just going up, up, and up. So, for example, chapter 7, verse 17, water increased. Later, the same verse, the water prevailed and increased greatly. In verse 18, the water prevailed more and more. In verse 20, the water prevailed 15 cubits higher. So what you've got is a picture of when the water started coming, it just kept coming. It kept getting deeper and deeper and deeper. And then it leveled out, and the rain stopped, the floodgates of the deep stopped, and basically everything had been accomplished that the flood was designed to do. And then you go into chapter 8, and now you see a monotonic or steady decrease in seawater level. In verse 1, it says the water subsided. Verse 3, it says the waters receded steadily. Verse 5, the waters decreased steadily. So you've got a picture now of just a slow, steady drop in water level. There's no oscillations, there's no complexity here. It's just simply going down. And this total duration of the Genesis flood event is roughly 1 year. So again, from a geologic point of view, this is a very simple event. The waters came up, and then the waters receded, and the time frame was approximately 1 year. Okay, on the next slide, we're going to start contrasting that with the geologic record. The geologic record is extremely complex, and I'm going to show you that there are many depositional processes. And by depositional processes, I mean ways in which the sediments get laid down. That happens in a number of different ways, and we're going to go through a bunch of examples. And there are many structural processes that happen to these sediments once they're deposited. Structural processes would be things like faulting, folding, erosion, mountain building. There's lots of things that happen to these sediments once they're laid down. And also, there are many thermal and chemical processes that operate on these sediments once they've been emplaced. And we're going to go through examples of each of these three levels of complexity. There are two places that I want to focus on. The first one is going to be eastern Utah. And I picked eastern Utah because it's the world's best geologic training site. It's the place where universities and oil companies, people really throughout the world go to look at and study and understand sedimentary geology. So at least for the sedimentary side of geology, this is the best place to go. And one of the reasons for that is you have all kinds of stuff that's been laid down. There's lots of depositional environments. You can see a lot of these things in 3 dimensions because there's all these cliffs and stuff. It's been eroded and faulted to the point that you can see stuff. And then the last point, it's in a desert, so it's not completely covered with vegetation and lakes that would hide the geology. And then when we get done with eastern Utah, we're going to go back to where I work, and we're going to go to the North Slope of Alaska and talk about biodeposits. And the reason we're going to talk about the North Slope is it's the biggest and best hydrocarbon province in North America. And there may be some Canadians like Hugh that might disagree with my assessment of biggest and best. I think it is. Let's start talking about eastern Utah and some of these examples of geologic complexity. And we're going to start with what we call evaporite deposits. And by the way, I'm going to be using some big geologic words, and I'm going to try to bring them down into layman's terms. But geology is kind of like medicine. A lot of the things we know and simply understand have very complex names. And I'm going to try to get away from the complex names and just use terminology we all understand. These evaporite deposits that I'm going to start with, these are desert salt flats, kind of like the ones out in Mono Lake or Salton Sea area of California. This is where water runs out into a desert and evaporates and leaves salts of various kinds behind. We're going to get into limestone, and limestone is a slow organic deposition process. These are critters of various descriptions that convert calcium in the dissolved in the ocean water and carbon dioxide from the atmosphere into calcium carbonate, which is limestone, and then these critters die and become part of the rock. And as I'll go through several times in this talk, limestone only is formed in shallow, clear water, warm marine environments, kind of like Fiji. And then there's another good geologic word called fluvial. And fluvial just simply means it's deposited by streams and rivers. So we're going to get into a number of these braided stream and fluvial deposits. Then we're going to look at some of my favorite rocks in Utah are actually these are what are called aeolian dunes. And aeolian is a fancy word for windblown. So these are like the Sahara Desert, these gigantic sand dunes that are not deposited by water but are deposited by wind. Then we have examples of delta where a river runs into the ocean, and then beach deposits. Coal swamps, well, we have a number of these that you'll see. And that's pretty self-explanatory. There are stagnant swamps where the plants die, they fall into the water. There's really not enough oxygen, so the plants don't rot. The plants are preserved and eventually become coals. And then there are deep marine shales. That's kind of the muddy yuck that is found at the bottom of the ocean, where it's at least hundreds of feet, if not thousands of feet deep. So in very deep water, you deposit these kind of muddy deposits that eventually become shales. And I'll be showing you multiple cycles of each one of these depositional environments in eastern Utah. It's a very complex place. And it includes Arches National Park, Canyonlands National Park, and a bunch of the pictures that I'm going to be showing you. In fact, it's about all of them that I'm going to be showing you come from this little circled area. So this one area of Utah is just absolutely fabulous geologically. And on the right-hand side, if you look at the stratigraphic column, I really like this one because it uses more everyday terms rather than the geologic buzzwords to describe these different events. And if you want to look on the left-hand part that talks about the time units, you have these different geologic ages like Pennsylvanian, Permian, Triassic, Jurassic, Cretaceous. This is the period from about 300 million years ago to about 50 million years ago. And so we've got about 250 million years of depositional environment that's occurring in this Arches National Park area. And what I want you to focus on is not the radiometric dating of how old these things are, but let's take a look at the different kinds of deposits that have been laid down in this part of Utah. And I want you guys to start from the bottom, because a geologist always looks at the lowermost rocks first. That's the oldest stuff, and then the newer stuff is deposited on top of the old stuff. So a geologist will always start from the bottom and work his way up, whereas a drilling engineer thinks the other way. He doesn't care about the stuff on the bottom. He's worried about the stuff on top that he's got to drill through to get down to your biodeposit. So the driller starts from the top, but we're geologists today. We want to start from the bottom. And if you look at this, what's called a paradox formation, down in the bottom of the stratigraphic column here, that ends up being a salt deposit. It's about 1,000 feet thick that underlies what's called the Paradox Basin, which is this southeastern Utah area. So there was 1,000 feet of evaporite salt deposited that all these other deposits were then laid on top of. And we're going to start working our way out of the salt into this Honaker Trail formation, which, if you read on your little geologic events column, it's got limestones, sandstones, shales, and salts, all in a shallow sea environment. That'll take us then to the next slide. This is Highway 191, just northwest of Moab, Utah. It's at the entrance to Arches National Park. Can you guys see the little yellow arrow there that says 6 feet? Okay, if you look close, there's one of our guys that's he's got a pair of binoculars and he's looking up at this rock section. So that's how I know this is 6 feet. And what we're looking at here, this is the Honaker Trail. This is a sandstone deposit. And if you look closely, you can see what looks like a set of stairs. Going from left to right, the sandstone has been down thrown a total of about 40 feet in about a 100-foot horizontal run. So this is what a geologist would call an echelon faulting. This fault was accommodated by a series of stuff that looks like stair steps for all practical purposes. Okay, let's go to the next slide and let's look at it in some detail here. This is the same place, but just a little closer. And what I want to focus on here is how these rocks were faulted. The little stair steps, you can see the faulting of the Honaker Trail sandstone. It goes from, say, southeast up to northwest, and you can follow these fractures. But if you look at the rocks themselves, you can see that the sediments are flat-lying, and they haven't been deformed or twisted at all. So the sandstone on top was hard rock. It had been deposited as just loose sands and silts and had then been compacted and cemented into hard sandstone rock. Then later, once it was hard sandstone rock, the faulting took place. So, these horizontal layers stayed horizontal. They didn't twist or deform. They shattered like plate glass when you hit it with a hammer. So this was brittle deformation. The rock shattered. But if you look at the shale layer in the middle, that's that kind of a darkish brown band. Does everybody see that? That squirted like the kind of toothpaste we had as kids. It had the green and red stripes in it. And you'd squirt the toothpaste around, but the green and red stripes would sort of stay in position. Well, this shale extruded. It just squished and moved in what's called ductile deformation. So this shale was not compacted. It was not rock when this faulting took place. It was still kind of a little bit loose. But so this is what a geologist would look at to see when the rocks were deformed, in this case fractured. And you can tell the sandstones had become hard rock, but these clays were still kind of soft. The reason I bring this up is because it takes a long time to cement sand into sandstone. But we know this sand was hard rock when it was broken up. Okay, on the next slide. This is a really neat place. This is the Moab Fault. And it's, again, right at the entrance to Arches National Park. The formation on the left is the Honaker Trail limestone. And this is about 300 million years old. And you see just like somebody took a knife and just sliced from northwest to southeast, and up against the Honaker Trail limestone, you have this Entrada sandstone. And this sandstone's about 180 million years old. So we have over 100 million years of missing section occurring in this giant fault zone. So what's happened is the rock on the right-hand side has faulted, and it's gone downward. And in this case, it's slid downwards over 2,000 vertical feet. So you've got this Entrada sandstone, which in most places is a couple thousand feet above this Honaker Trail limestone. Well, in this case, if they're juxtaposed, they're right next to one another. Okay, let's go to the next slide. The guy on the left-hand side, he is a structural geologist. Bob Krantz is his name. And he was explaining what these guys do. The structural geologists, they're specialists in how rocks break and fold and fracture and deform. And he's explaining what went on here at the Moab Fault Zone. What we can look at is if you look at remember the previous slide I had on the Honaker Trail sandstone where the rocks fractured brittly. Well, this limestone did the same way. The limestone didn't deform at all. It was hard rock when this faulting took place, and it stayed with its horizontal layering. It just broke again like a plate glass window, and this sandstone on the the right-hand side kind of got all busted up and deformed. But this Honaker Trail limestone just stayed intact, and it's like somebody took a giant knife. So what happened here was we had brittle deformation of the Honaker limestone, and then this 2,000 feet of faulting was all eroded. This is all on the surface now. So originally there was 2,000 feet of rock at least above this limestone. It's all been eroded flat. So now this is, although we're in a little gully here, this is basically flat-lying rock. So again, you've got a complex structural feature here. Cement the rock hard, you break it and displace it by several thousand feet, and then you erode it flat. This all took a long time to do. Now there's on the next slide, there's a cross-section of this area. It's called the Moab anticline. I should mention that one of the reasons we're looking at this fault, the Moab fault, is we have a very, very similar feature at Prudhoe Bay. The northern end of the Prudhoe Bay field is defined by what we call the North Prudhoe Bay Fault, and it has over 1,000 feet of throw, and it juxtaposes the pay rock, the sandstone we produce oil out of at Prudhoe Bay, with the marine shales. It's just as sharp a feature as this Moab fault. So we've got, again, 1,000 feet plus of fracturing and faulting on this one side and intact rock on the other. So it looks a lot like this Moab fault zone. Okay, slide number 17 shows a cross-section. And this is if you could slice the earth open and kind of look at it on the side like you would slice open a layer cake and look at the different layers. Well, that's what we've got a picture of here. So you're looking at a cross-section that runs from the northeast to the southwest, and if you could imagine just taking a vertical slice of the earth. And what I want to show you here is how these sediments were all laid down just like a layer cake. They were laid down flat originally, and then all this structure was superimposed on top of this layer cake deposit. And if you look right in the middle on the bottom, you can see this Moab fault zone. And this Moab fault has this 2,000 feet of vertical displacement, so the stuff on the left-hand side has been shoved upwards 2,000 feet, and then erosion has taken place, and it's made this whole area basically flat. So again, a very complex picture of a real geologic feature. So going to slide 18, we can kind of give you a chronologue of what happened in this Moab anticline. So we had, in this area, roughly 10,000 feet of flat-lying sediment deposited, and this was deposited on top of this 1,000-foot salt zone that I mentioned earlier. This took about 200 million years to deposit all this sediment. And during that time frame, the Honaker Trail Formation was compacted and cemented. It became brittle rock. And then this massive faulting took place, over 2,000 feet of displacement. The entire region was tilted, and then massive erosion took place, and it removed thousands and thousands of feet of sediment until now it's all on the surface. And the key point is this cementation, faulting, tilting, and erosion all happened long after the sediments were deposited. And this complex depositional and structural history just can't be explained by the simple flood event. And one of the things I want to point out also, and we'll get into more of this in just a minute, is a lot of these events can't be explained by a flood. For example, these big salt deposits, these evaporites, you have to have water running out into a desert basin and evaporating. The limestone has to form in shallow marine water. It takes a long time for all these critters to grow and die and become rock. And I'll show you all these depositional environments in a minute. But the fluvial systems, the streams and rivers, that's not a flood. These are just steady meandering stream channels. They're not flood events. They're kind of steady depositional systems like modern rivers do. And then we have these just gorgeous Aeolian or Sahara Desert dunes that are interlaid with all these things. So it's not only very slow processes, but there are just all kinds of different depositional environments that are not related to big flood events. Okay, we got the delicate arch one up. First thing I want you to notice there is, again, a little arrow. That shows a person down there. That's a 6-foot-tall human being, and that little bitty arrow right next to it, if you can see him. And this whole arch must be, it's got to be about 80 feet. And this is just part of the Entrada sandstone, which is one of these gigantic Sahara Desert kind of deposits. And if you look on the right-hand side, what you'll see is that same delicate arch with the Entrada sandstones, and underneath it you've got hundreds and hundreds of feet of what's called Navajo sandstone. And the Navajo sandstone is also one of these Sahara Desert type Aeolian deposits. It's wind-blown. It's not laid down by water. These two formations are done in these gigantic deserts, just like the Sahara. When you get on top of where Delicate Arch is, this is what you look at. You're looking basically at this Navajo sandstone. And this, again, is about 300 feet thick in this area. And you can clearly see, or at least a geologist can clearly see from looking at this picture alone, that these were wind-blown, not waterborne deposits. It's just gorgeous topography, and you can see why people like to come to southeast Utah to look at the geology. Okay, the next slide. This is, again, Delicate Arch. The Entrada sandstone, just like the Navajo, is over 300 feet thick. And here's your 80-foot arch right there. And you can see, just on what we're looking at, there's probably about must be about 100, 150 feet of sediment. Okay, next slide. And even geoscientists and engineers need to eat. So if you're wondering what this is a group of 23 geologists, geophysicists, and petroleum engineers. We're on this outcrop study here at Southeast Utah, and we're studying these depositional systems, but right now we're just having fun. And that's actually me in the blue shirt in the left-hand center of the picture, digging into my backpack because it's lunchtime. The reason I'm showing this picture, again, is to give you a feel for just how gigantic these sand dunes were. So if you can imagine just the biggest dunes you've ever seen, just like in the guts of the Sahara Desert, that was the environment in southeast Utah, all those many, many years ago. Okay, slide number 23. I've got some just descriptions of these Aeolian deposits. Okay, they're huge dunes, just like the Sahara Desert, and they're very easy to tell from a waterborne deposit because these wind-blown sands are very angular, and they're frosted. There's so much rubbing of the sand grains that they get frosted, so they get kind of whitish looking. And instead of some very thin bed sets that we're going to see a little bit later in the riverborne deposits, rivers and deltas, these just have massive bed sets in these Sahara Desert kind of deposits. They're just huge. and they don't look anything like what you're going to see later when I start showing you water deposits. These deposits run all the way from New Mexico to Montana, so it just covered a huge area. And again, the Sahara Desert's a pretty good analog. There are no aquatic fossils found in the Entrada or the Navajo. They are just deserts. But they are separated by river and marine shales. So the ocean did transgress and cover all of this stuff up between the time when the Navajo was deposited and the Entrada was deposited. And then the other thing I want to point out about these Aeolian deposits, these gigantic dunes, is there's no way Noah's flood could make these kind of sandstones. They had nothing whatsoever to do with water. These are laid down by wind in a very arid environment. What it is, it's basically erosion of some of the softer parts of the rock. And there's one particular member of this Entrada called the Slick Rock Formation that it seems to be very prone to making these arches. But I think it's the way that whatever little water did run through these things basically cemented some of the sand grains a little bit tighter than others, and so it was more resistant to erosion. And it's the erosion of current wind and rain on these ancient sandstones that's causing these arches. It's very unusual. I'm not sure of other places in the world, just a handful, that would have these kind of deposits. So going forward, we're going to go forward about 100 million years here, and we're going to go up into the Jurassic, which is this middle of the age of the dinosaurs. You're looking at what's called the Morrison Formation. Now, can you see the difference between these gigantic Sahara Desert sand dunes and what we're looking at here? This is very much layer cake, and you've got alternating layers of sandstone and siltstone. Every once in a while you'll have a little bit of mud in there, but they're pretty thin layers, but there's lots and lots and lots of them. And every one of these layers represents a stream or a river wandering around and changing courses. And sometimes you get thick, what are called distributary channels, and that's kind of the thick one in the middle of the picture. If you think of these kind of formations, they're almost like sort of a deck of cards that you look at from the side. There's lots and lots and lots of little thin layers. And this is typically a dead giveaway that you're dealing with a fluvial or a flowing water system, either streams or rivers. And the reason that we study this particular interval, this member of the Morrison, is actually an excellent analog to the uppermost 150 feet of the Prudhoe Bay Field. Our Zone 4 is about 150 feet thick, and it's a wonderful oil reservoir, and it looks, as best as we can tell, very, very much like what you're looking at in this picture. It's just buried 9,000 feet deep in the Arctic. And also, don't know if anybody's interested or not, but I'm the guy in the hat in the lower left-hand corner. And we're talking with a reservoir engineer and a geologist there about this particular formation and why it looks like Prudhoe Bay. This picture really shows a very clear difference between these Sahara Desert type of deposits and these waterborne deposits that were laid down by flowing fresh water. If you go to the next slide, we're working our way up in the structure. This Morrison Formation is capped by this ugly thing called the Mancos Shale. If you see the mountains in the foreground here, that's all Mancos Shale. This is Badland stuff, and this is a deep marine shale. It was deposited in water that was at least hundreds of feet thick, possibly a couple thousand feet deep. So this is a deep marine environment. This is the muck that accumulates far offshore. And the Mancos Shale can be hundreds to as much as maybe 1,000 feet thick or more. And this is the kind of rock, actually, that we're interested in that becomes good source rock for generating oil deposits. But if you can think of this stuff as being on the bottom of a deep ocean, then you've got a pretty good picture of how the Mancos Shale was laid down. And it's on top of all these river sediments and desert sediments that I've shown you earlier. And then if you go on top of the Mancos Shale, go to the next slide, in this place called Toucher Canyon, these are Cretaceous age, they're fluvial and deltaic sands, and that just means they're laid down by fresh water and then by the fresh water as it ran out into the ocean. So you've got rivers and river deltas here, and they're intermixed with the siltstones and shales. And this is an excellent analog for about the bottom 100 feet of the Prudhoe Bay field in what's called Zone 1. And that's the reason we study these rocks in Utah, because it looks a lot like the base of the Prudhoe Bay Reservoir.
When you're looking across, say, I don't know, you're standing somewhere relative to the Honaker Trail or whatever, you see all those above you as you're walking through. Is there a place where you know that it's one on top of the other like that? You know what I mean, Pat?
Well, actually, to go through this, you're looking at something close to 10,000 feet of sedimentary deposition here, and you don't see it all in one place. You can sort of track it along on the surface, and then it'll disappear, and then something else will come up above it. So in order to get the entire column, you actually have to maybe drive maybe 20 to 30 miles to see the entire thing laid out. But you can see in places a couple thousand feet at a time where you've got these big cliffs, but you don't see more than a couple thousand feet at any one spot. So there's no single place that all of this is exposed, but you can find it all when you drill down in well bores. And there's several fairly decent oil fields in the Paradox Basin where they've drilled through all of these formations, but you can't look at them on the surface at one particular spot.
No, I was just wondering if you know, like you said, if you drill down, you do find that same kind of formation.
Oh yeah. Yeah, this stuff definitely exists in the underground, and the beauty about eastern Utah is you don't have to go very far before you can actually see this stuff above ground.
Yeah. Now, is that how it is across the whole world, kind of thing, Pat? Or
yeah, this is pretty representative of what happens most everywhere. And the reason I picked Southeast Utah is because number one, I had all these neat pictures, and then number two, I had personal familiarity with it. But yeah, the geologic record looks like this in a lot of locations. Sometimes it's not this complex, but this is fairly representative of what we actually see in the geologic record. Well, it's true that I don't think there's any single piece of the world that has every single time on it, because well, the history is very complex. Sometimes sediments aren't being laid down. Sometimes sediments are being eroded. For example, if you're in a mountainous area, you're losing sediments, and if you're in a valley area, you might be picking up sediments. But that doesn't make it a myth, because, like for example, in both Utah and Alaska, we can drill through, in both cases, over 12,000 feet of sedimentary rock. That rock is really there, and it was laid down by subsequent, one geologic process following another, and you can trace these processes over long, long areas. So while it's true that not one single spot in the world has everything, we can find every age represented in multiple places on the planet. So if you go to the next slide, we can walk our way through all this. And again, we're going to be good geologists. We're going to start from the bottom. And on the left-hand side, what I've got is this kind of simplified geographic column that shows all of the different deposits. And on the right-hand side, I've got a description of exactly what those are. And where I've got the red dots and then the descriptions on the right-hand side, those are the pictures that we've looked at. So we started from the bottom and we worked our way up. And before I start describing each one of these things, do you guys see that little black bar kind of in the middle of the slide? Think of that as a 30-story building. That line is 100 meters tall, so that's a 30-story building. So that'll give you some scale as to how thick these things are. The first stuff we looked at was the Honaker Trail Formation, and that was limestone. Again, that's a shallow, warm marine environment. Then we looked at sandstones, so those were deposited by rivers and streams. Okay, then we come up about, that would be a good 100 million years, and we're going to come up now into these, the Navajo sandstone, and that's desert dunes. That's the Sahara Desert. We're going to, then the next stop, the next red dot, is the Entrada sandstone, and Bob actually spotted this. If you see the little diagram of an arch they've got in the slick rock member, that tells you exactly which of these formations makes these arches. So we've got the desert dunes with the arches, in the Entrada sandstone. And then we go into the Morrison Formation, and this lower Morrison, that's the rivers and streams that looks just like Prudhoe Bay's Zone 4. And then we work our way up from this into the Cretaceous time frame, and we get to the Mancos Shale, and that's deep marine shale. That means that water was hundreds to perhaps a couple thousand feet deep. And then on top of that, in the upper Cretaceous, we've got rivers and streams, and then we've got deltas. So what I want to communicate here is that this is a very complex layering scheme. There's a lot of stuff going on. This is not at all simple. So if you go to the next slide, we can summarize all this. Question number one, could the entire geologic record have been laid down quickly thousands of years ago in a global flood? And the answer is, there's no way this happened in Utah. We have many depositional environments. In some of these depositional environments, the flood simply can't generate. And again, the Sahara Desert sand dunes are an excellent example of that. Some of these deposits form very slowly, and that especially includes the limestones and the coal seams. And if I've convinced you of nothing else, I should have convinced you that there are many complex alternating sequences of these different stratigraphies. And then structurally, what was going on is complex faulting and subsequent erosion. So again, an extremely complex picture, and there's just simply no way that the simple, geologically simple flood event could have accomplished this geologic record. Okay, let's change gears and leave the geologic record in Utah behind us, and let's go way up north. Let's start talking about biodeposits. And slide 31 here is a map, basically it shows you the area we're talking about on the north coast of Alaska. And the fields I'll be discussing, the Prudhoe Bay field is, you can see the one arrow pointing to it, and that's the Trans-Alaska Pipeline that's headed straight south from there. The little line with the dots on it, that's the oil pipeline. And it's all north of the Brooks Range, a very, very flat-lying swamp, basically just north of the Brooks Range. It's called the North Slope because it slopes gently into the ocean. If you look at the next slide, I've got a geologic column for the North Slope, and here you actually have a time frame of these things. That middle column called MA, that's millions of years ago. So the base of this Mississippian formation is 360 million years old, and up near the top you got about you got a pretty big gap. It looks like about 65 million years where there's not much sediment laid down. So pretty well ended. Deposition more or less ended about the Cretaceous time frame. And what I've got in the little pictures in the middle, those are geological representations, kind of cartoonish, of these different environments. You've got sandstones, limestones, shales, and they've got these different names on there. And then on the right-hand side, these are the oil fields that are associated with those different depositional systems. For example, the Endicott field is it's a big offshore oil field, offshore in the Arctic Ocean, and it's producing out of these Mississippian rocks. You work your way up into the Lisburn. That's a huge limestone deposit that I'll talk more about later, and the Lisburn oil field produces out of that. In the Permian and Triassic time frame, that's the Prudhoe Bay field, which is North America's largest oil field, and that's nominally, say, 250 million years ago. We've got then the Sag River field above that, and then a really interesting field called Alpine at the top of the Jurassic, and I'll talk a little more about Alpine. Going up from there, the Kuparuk River field is North America's second largest oil field. That's just to the west of Prudhoe Bay and these Cretaceous rocks. And then you can work your way up into these heavier oil deposits in the West Sac and Ugnu that are still really not on production. So those are the oil fields that are involved in Alaska's geologic column. Now let's take a look at the depositional environment that these oil fields were laid down in. And at the very base, again, we're going to be good geologists. We're going to start at the bottom because that's how these sediments were laid down. In the Mississippian time frame, these Endicott sandstones, there's two hydrocarbon accumulations that I'll talk about. Actually, I'll talk about one in a little more detail in just a second. those were laid down in fresh water. Those are fluvial deposits. So again, at the very, very base of this sedimentary column, right on top of the granite, the basement rocks, you have river systems. Going up above that into the Lisburn, this is a limestone that's 1,500 feet thick and about 1,000 miles long. It's a huge deposit. And again, limestones are only formed in shallow marine environments. And going up into Permian times, that was a deep marine shale, kind of like the Mancos Shale. It only forms in deep water. And then you get into the Saddle Roach at the Prudhoe Bay Field, and those are delta deposits and river deposits. Okay, above the Saddle Roachet in the Schublick Formation, that's a limestone that caps the Prudhoe Bay Reservoir. So it's back into a shallow marine environment. And then the Sag River Sandstone is also a shallow marine environment. On top of the Schublick, you have this Kingak Formation that's Jurassic aged, and that's a deep marine shale. Again, it looks a lot like that ucky-looking stuff in the Mancos. It's just a sticky, deep marine shale, but it's very important because the Kingak is full of dead critters, and we're going to talk about source rock in just a minute. But these dead critters in these deep marine shales are what forms the oil. Okay, we then go into the Alpine field at top of the Jurassic, and that was a shallow marine environment. It's just right next to the coast. And the Kaparic River sandstones in the lower Cretaceous, again, are kind of shallow marine systems. The shale up above that in the middle Cretaceous, that's a deep marine system. And then we go into shallow marine systems, and then up all the way going into the top of the Cretaceous, we now are getting into river systems. We're back into these fluvial deposits, and they actually have coals in them. So we're looking at swamps, basically freshwater swamps. So you can see kind of like Utah, a complex series of alternating depositional systems with rivers at the bottom and shallow and deep marines back into rivers and deltas, shallow marine, deep marine. Ocean depths are alternating, and finally at the very top of the column you get back into freshwater deposits. There's a lot of complex history that goes on here, and people have spent a tremendous amount of time and effort trying to understand what happened on the North Slope, because it's economically it's very important. There's billions and billions of dollars that have been invested up here trying to develop these fields and understand what's happening. And I want to go through some of this, especially when I talk about the Lisburn group. I'm going to talk about some of this complex history that's gone on. But there has been episodes of mountain building, the plate tectonics where things have moved away, where these sediments have slumped and fallen, subsequent erosions happened. The Brooks Range got built to the south. There's just a lot of separate events that have caused these different things to happen. Okay, well, let's go on then to the next slide. And again, we're talking about biodeposits, so I've given you a picture, a brief one of the complex geology. Now let's take a look at the different kinds of deposits that we've got. At the very bottom, in what's called the Kekiktuk sand, as part of this Endicott group, we're going to have coal and natural gas, and I'm going to show you some examples of that. And then in the northeast corner of this section, in the Endicott group, we have this big offshore oil field. In the Lisburn, we've got a huge amount of limestone that's filled with several billion barrels of oil. Up in the Saddle Roachet, that's oil and gas. That's America's largest field. And then in the Schublick Formation, we've got limestone and oil. In the Jurassic, the Alpine field, that's full of oil. And then in the Kaparic River Sandstone, Lower Cretaceous, that's also oil. Up in the Upper Cretaceous, going into the Tertiary time, we've got oil, and then we've also got coal. So you've got a lot of different kinds of biodeposits going on. And now let's start talking about some of these. The Alaska North Slope geologic record, it's very complex. We've got many depositional environments. Some of these things are very slow. These limestones and coal seams in particular take a long time to form. We've got these many complex alternating sequences of different water depths, and sometimes it's fresh, sometimes it's salty. We've got complex faulting, tilting, and erosion, just like we had in Utah, and I'll show you some examples of that in a minute. Okay, we're going to go through 3 examples of biodeposits. I'm going to show you how oil got into the alpine field. We're going to take a look at some coal in the Kekiktuk Formation, and then I'm going to talk about the formation of limestone in the Lisburn Field. Okay, the next slide shows what's called a transformation ratio, and basically you can just think of this as something that's either undercooked or overcooked. And what we're looking at here is this Kingak shale that looks a lot like the Mancos shale that I showed you in Utah. It was a deep marine system. It was just full of dead critters, and these are typically very, very small animals. We're talking about the phytoplankton here, and very, very small multi-celled animals. Some of these are one-celled, but they're all just extremely small, and they exist in vast amounts in the ocean. And when these guys die, they settle to the bottom. And if you were to look at this particular Kingak shale, this TOC, that means total organic carbon. That means that 5% of the total mass of this shale is dead critters. So, for example, this Kingak shale is about 2,000 feet thick, and that means we have, if you were to isolate them all and separate the silts and shales out from the dead bodies, we would have 100 feet of dead microscopic animal bodies. That's a very, very rich source of organic carbon, and that will become the source of oil, but it's got to be cooked. We've got to convert the fatty deposits in those dead critters into liquid hydrocarbons that we can then produce. And so that's what's called the transformation ratio, and this graphic shows contours of what fraction of those dead critters have actually been cooked into oil. And we're looking at the outline on the right-hand side. That's the Kaparic River field. And up into the east and northeast, they have never had any oil sourced from the Kingak shale. But in the alpine field, which is that little outline to the on the left-hand side, that's a billion-barrel oil field. It's one of the newest oil fields in the Arctic. And that oil came from the Kingak shale. So the oil in this billion-barrel field was cooked. And the contour line shows that it's just barely hot enough at the alpine location to start cooking these critters into oil. And that explains why we never saw any Jurassic oil farther east. So you can just think of this as a long, call it a crock pot. It took a long time at a very low setting, but the crock pot finally cooked these dead critters into oil that we could then produce. So the next slide describes this. There are no Jurassic oil fields in the east. Even though this Kingak shale is found all across the North Slope and it's thousands of feet thick, Alpine is the first Kingak-sourced oil field. And it only has oil in it because it finally got hot enough for long enough to cook these critters into oil towards the southwest. Okay, now I'm going to get out of the oil and I'm going to get into coal. The next slide shows the Kekiktuk Formation, and it's kind of a complex picture here. The middle track, this is the depth. There's one that says depth and one that says elevation, and the first number you see is 11,500, then 11,600, 11,700. That's how deep this oil well is. So we're looking at measurements from an oil well that's drilled, in this case, to 12,000 feet deep, and I'm showing you this section between 11,500 feet and 11,700 feet. And what we do is when we get the wells drilled, we run these recording devices into the hole on the end of this long cable, and then we take all these different measurements. And this is a petrophysicist or geologist or petroleum engineer would look at these readings, and that would tell him what kind of depositional system he's looking at and what kind of fluids exist in the rock. And I'm not going to go through all of these things, but I'll just say the track on the left-hand side, that's natural gamma radiation that the formation is emitting. And so we've got a record of how much basically thorium, uranium, and potassium is occurring in the formation. And those things are typically associated with silts and shales, and they are not associated with sandstones, and they are also not associated with coals. So we can see a number of these things where they're highlighted in yellow, where there's no natural radiation to speak of in there. So those are probably coals or sandstones. If we look at on the kind of on the far right-hand side, what we're measuring is how fast sound travels through these formations. And coals are very weak, and sound travels very slowly through these things. So, but sandstones are very hard at this depth, and sound travels very fast. So we can look at basically the sonic travel time and tell if it's a soft or a hard formation. Kind of the track in the middle, we bombard it with either gamma radiation or neutrons, and those responses vary as well. So we can take all this complex information and interpret it. And what we found is on the left-hand side, I've got coal seams illustrated here. We're going to again start from the bottom as like good geologists. There's one there's 8 feet thick, work our way up another about 100 feet, and there's one that's 10 feet thick, 3 feet thick, and then there's 3 little thin coal seams that are each 3 feet thick, and then the one on top is about 14 feet thick. So what we've got in this 200 vertical feet of sediment, we've got, what is this, 1, 2, 3, 4, 5, 6, we've got 7 separate coal seams that have a total thickness of about a little over, about 40 feet. And then right in the middle of all this coal and shale, we have a 40-foot thick sandstone that's filled with natural gas. So the thing I want you to think about here is 12,000 feet deep, we've got coal swamps. And then we've got freshwater sandstones that were laid down. And again, this took a long time to do because each one of these coal seams represents many years of plants living, dying, and falling into stagnant water. So if you go to the next slide, this kind of describes what's going on in the Prudhoe Bay State number 1 well. And this really is a pretty neat well because this was the discovery well for the Prudhoe Bay field. It was drilled in 1969, and it was the last chance for the Alaskan Arctic. And it was pretty interesting because we had drilled, I think, 17 dry holes in a row, and they were getting set to fly the rig off the slope and basically abandon Alaska as a petroleum province. But they had time to drill one more well. And before they walked away, they drilled this thing, and they hit the Prudhoe Bay field. So it's a pretty neat well, and the rest is history, and that's kind of why I'm up here. But in this Prudhoe Bay State number 1, we had over 12,000 feet of sediments. Now, at the bottom 300 feet of this, over 300 feet, was a freshwater deposit that's full of swamp coals, shales, and these river sands. And this interval contains lots of coal seams, and it contains sandstone, and this sandstone contains gas that didn't come from coal. So we've got a picture of slow deposition, multiple cycles, and this all took place over a very long time, and it took place in fresh water because these things cannot be laid down in salt water. So again, many, many, many years of freshwater deposition. Next slide, we're going to talk about the Lisburn limestone. And this is probably the biggest biodeposit on the North Slope. This is a huge limestone deposit. It's about 1,000 miles wide. It runs all the way from northwest Canada to Russia. And it's about 1,500 feet thick on average. And it took place over 60 to maybe 80 million years of deposition. And it's a very complex history. The best way to think about this Lisburn limestone, if you go to the next slide, think about it as a good analog to the Persian Gulf. Because the Persian Gulf is also a very big place, and actually this lowermost 1,000 feet of the Lisburn limestone is extremely similar to the Persian Gulf. And what I've got is a cross-section of how the geologists have interpreted the limestones to have been built. And if you start from the left-hand side, that's the onshore part. That's where you're getting into sand dunes and these salt flats. They're called sabkas. And if you go to Kuwait or the United Arab Emirates or Saudi Arabia, you'll see this kind of flat-lying, salty, really ugly-looking sandy land inland from the beach. And then you'll have a beach, and then it'll go offshore a little bit, and the water is circulating very slowly in what's called a restricted platform. It's kind of like a lagoon. And this water is just full of all kinds of different critters that are laying down seashells and corals and different things that are going to eventually decay and form this carbonate rock called limestone. And it's pretty interesting. I've gone snorkeling in the Persian Gulf in this kind of environment, and the water gets so salty that it's very, very hard to get down. It's a restricted flow, and so the salinity gets very high, and the water gets very dense. But it's just full of critters. And then you go offshore a little farther, and you get to this shoal, and that's kind of almost like a barrier reef. And the two little lines you see, that's high tide and low tide. And so this stuff can actually be exposed at low tide, but it's covered at high tide. And then as you progress your way out into the basin, you get into the open marine systems. And so that would be like you're heading towards Iran in the Persian Gulf. So again, this is very, very similar to today's Persian Gulf. Similar in size as well. This was a huge deposit. Okay, the next slide shows some pictures that were taken in the Franklin Mountains. It's part of the Brooks Range in the Arctic National Wildlife Refuge. And here, instead of being buried 9,000 feet below the surface, all of these sediments are exposed. And I'm not expecting anybody to know any of these fine terms, but a carbonate geologist doesn't have any trouble at all in telling what kind of environment, like we saw on our previous slide, is occurring. So, for example, this mudstone in the middle of the slide here, it's about 3 or 4 feet thick in this picture. That's similar to that kind of restricted lagoon that I talked about earlier, where the water gets very saline and the circulation's very, very slow. And it's very easy. You can see these sharp breaks between these different depositional systems. So the geologists can study these and figure out how long these things took to form and exactly what kind of environment they formed in. Okay, if you go to the next slide, and this is one that's extremely complex, and I'll apologize for it, but the thing I really want you to get out of this is that these geologists can look at this kind of a limestone environment and come up with all kinds of complex histories. And what I want you to focus on is this one on top. There's a red box with an arrow going to a little squiggly kind of greenish slab. Well, we're going to talk about that. That's the uppermost part of the Lisburn limestone. And that we're going to talk about now some structural complexity for what happened in the Lisburn. Okay, go to the next slide. And, okay, what we've got here is a limestone that took maybe 60 to 80 million years to form. It's 1,500 feet thick. And we're going to focus on that little wavy green line that I showed in the previous slide. That's the top of what's called the SAZ. It's a fancy word. It means subaerially altered zone. And what that means is this reef, this limestone reef, was actually lifted up above water level, and then rainfall, basically acid rainfall, etched out and leached out this limestone. So it was eroded with this unconformity, and then it got rained on for a long period of time, and it dissolved out a lot of the limestone. It then got reburied, and these sediments, in this case, they were shales that came in and deep marine system covered it all up. And then there was mountain building to the northeast. So this whole section was tilted at a pretty steep angle. And then during Cretaceous time frames, the ocean came back in, and the tides basically cleaned out and eroded all of the sediments and formed this thing called the Lower Cretaceous unconformity. So that red line initially was flat. And then those mountains sort of drifted back off toward Canada, and the whole basin subsided some more. And the thing tilted and then was covered by hundreds and hundreds of feet of deep marine shale. And then eventually the Prudhoe Bay oil field was laid down on top of this. But what I want you to get a picture of is a very, very long time to form 1,500 feet of limestone. Then it was elevated out of the ocean. It was eroded, and then it was rained on for a long period of time to leach out the limestone. Then it was buried, tilted, and eroded again, and then the whole thing was buried 9,000 feet deep. If you go to the next slide, it discusses the significance of all of this. You've got a complex depositional history with a lot of different carbonate environments, and again, the geologists can tell pretty easily what these are by just looking at at the different kinds of critters that show up in the limestone. This was deposited 1,500 feet thick, 60-plus million years. It was exposed to air. That acid rain dissolution took place. It was buried. Then what's called dolomitization happened, and that's magnesium-bearing waters from the mountains flowed through this and replaced some of the carbon with magnesium. And then that filled with hydrocarbons, with oil, and became an oil field. This formation suffered major uplift, major erosion, tilting, and subsidence. So the key conclusions here, the flood could not produce this thick limestone, and the flood could not cause these complex alterations of the limestone. So again, the Lisburn forms a very significant challenge to the concept that all of the sediments were laid down by Noah's flood. Okay, now I'm going to change gears completely from the chemical region, and we're going to start talking about temperature. The next map, the permafrost map of the state of Alaska, and I want you to look at the pink zone on top. That's the North Slope of Alaska, and that is a place where you have very, very thick permafrost. And the little arrow on the bottom, that shows you where I live, and we don't have any. But on the North Slope, this permafrost is 1,500 to 2,000 feet thick. And thermal studies have shown that this stuff took tens of thousands of years to form, and they also show that the permafrost has been thinning for about the last 10,000 years. So if you look at the next slide, you've got temperature profiles. These, again, are measurements of what does the ground temperature do as you go down and down and down into the Earth. And I'm showing it from the surface down to a depth of about 3,000 feet. And you're looking at temperature running from 0 Fahrenheit to 60 Fahrenheit. And the blue line is the actual data. The little pink line shows where that's 32 Fahrenheit. That's where you're going to have ice or permafrost. And if you look at this West Sac number 17 well on the left, that's in the Kupark field. We've got permafrost here to a depth of 1,800 feet. The North Prudhoe Bay State well in the middle of the Prudhoe field, we have permafrost down to a depth of 2,000 feet. So the ground is frozen very, very deep here. Okay, the next slide talks about some temperature data that we got from a ice core that we took in Greenland. This was a well that was drilled through 10,000 feet of ice and has the climate record for about the last 100,000 years. And if you go to the next slide, what you can see is a picture of what the temperatures looked like for the last 20,000 years on top. And each of these, the zero basically represents today's temperature, and when it goes to negative, that means the oceans were getting cold. When it goes to positive, that means they're a little warmer than today. This little ice age that it happened about close to 1,000 years ago, about 500 years ago, that was the time when the canals in Holland froze, and you could basically skate on the canals. It hasn't happened since. Go back a few hundred more years, this medieval climactic optimum, that's when the Vikings settled Greenland. So Greenland, you could actually live on it at that point in time. But what I want you guys to see from this slide is that the last 10,000 years has been pretty normal temperatures with these minor variations, and then before 10,000 years ago, it was extremely cold. And if you look on the bottom of the page, this is data from a several thousand-foot core in Antarctica, where it goes back many thousands of years, and in this case from 0 to 200,000 years ago. And what I want you to see here is that the last 10,000 years has been very warm compared to the previous 100,000 years. So from 100,000 years ago to 10,000 years ago, it was very cold, and only during the last 10,000 years has it been reasonably warm. So if you go to the next page, this is sort of explained. At Prudhoe Bay, the entire sedimentary column was deposited. The top 2,000 feet was frozen from 100,000 years ago to 10,000 years ago. And then the last 10,000 years, it's been slowly thinning or melting. So here's the concept. For the last 100,000 years, this ground has been frozen a half mile deep. It was frozen solid before, during, and after Noah's flood. So there's no way any of these sediments could have been caused by Noah's flood. So if you go to the next slide, question number 2, Could all the biodeposits have been formed thousands of years ago in a global flood? And the answer is not in northern Alaska. We have many depositional environments. Some are very slow, these limestones and coal seams that I talked about. There are many complex alternating sequences. The flood couldn't cook the kerogens to form the oil, the liquid hydrocarbon that we produce. The flood could not produce the limestone. The flood could not produce the permafrost. And the top 2,000 feet of the North Slope has been frozen solid before, during, and after the flood. Okay, here's a possible scenario for what happened in Noah's flood. First of all, I believe from a scientific point of view, it was a local flood. I think biblically, like Krista said, it could be either way. But scientifically, I think the location of this was the Mesopotamian floodplain. The fountains of the Great Deep broke open, and to me, that's the ocean. The Great Deep is the ocean, and the fountains of the Great Deep, what I would propose is there's potentially two sources of these fountains. One is the storm surge that occurs like hurricanes. The thing that really kills people usually is not the rainfall, but the tidal surges that come when the storm comes ashore. It brings a huge amount of seawater with it. And then also tidal waves. The Persian Gulf is a perfect shape to funnel tidal waves deep into the Mesopotamian floodplain. So the concept here was these a storm surge, possibly aided by multiple tidal waves, invaded deeply into this Mesopotamian floodplain, aided by massive rainfall. And then after God had achieved his purposes of judging mankind, the waters receded slowly back into the Persian Gulf, aided by a strong wind. And because this country is so flat-lying, the flow back into the Persian Gulf would be slow, and the wind would be necessary for evaporation. And the next slide shows a topographical map of the Mesopotamian floodplain. And what you can see is this area in green, which is less than 300 meters or about 1,000 feet of elevation. That encompasses a huge area that basically captures every place or geologic feature that we know about that was mentioned in the first 10 chapters of Genesis. So a flood that was approximately 1,000 feet deep would encompass this entire area shown in green. And that's what I think probably happened. Okay, the very next slide talks about what kind of record that would leave behind in the geologic record. And we would be looking at deposits only within the floodplain itself. And again, this being a very simple event, and it's going to be dominated by tidal waves supplemented by rain, it's got a very limited ability to generate a sediment load. And the concept here is, once something's flooded, increasing the water depth does very little to erode more sediments away. And the question you might ask is how much erosion occurs at the bottom of the lake during a rainstorm? Well, the answer is none. So once the water moves in and covers the land, increasing depth really doesn't do much to add to a sediment load. It doesn't do much erosion. And there's probably little remaining evidence of this geologic event. It's a very flat area. It's been reworked by wind and meandering rivers for the thousands of years since it happened. And it's also been disturbed by a long history of civilization and agriculture. So I don't expect to find much record of Noah's flood in the geologic record. I could wrap up on the last slide, which is overall conclusions. The Genesis flood is a very simple event from a geologic point of view. The geologic record and biodeposits are very complex, and the flood can't explain either the geologic record or the biodeposits. There's depositional complexity, how the sediments were laid down, structural complexity, which is what happened to the sediments, how they were folded, fractured, tilted, eroded once they were deposited. There's chemical and thermal complexity, like, for example, the formation of permafrost or the cooking of oils out of the kerogens. And then a key thing, the flood cannot produce these aeolian, which are the Sahara Desert type deposits, and it cannot produce limestones. And the flood cannot produce thick permafrost. So my conclusion from this would be the flood was restricted to the Mesopotamian floodplain, and the flood would leave little remaining evidence in the geologic column.
This has been a presentation of the Ministry of Reasons to Believe. If you would like to know more about other resources offered by Reasons to Believe, or have questions about issues related to science and the Christian faith, please visit our website at reasons.org or call us toll-free at 800-482-7836.